Hello everyone, and welcome back to Solutions to Linus Pauling's awesome textbook, General Chemistry. It's been a while since doing a video in this series, so I figured why not do this one from the beach? And after we're done, we can celebrate with some coconuts. No, I'm just kidding. I'm not really at the beach. But I did have a good time putting together these solution notes for you, which you'll find in the description below. So grab yourself a PDF if you like. Let me turn down these beach sounds and we'll get down to business. You can see the book cover right here, a nice Dover publication you can find in many bookstores. And the table of contents shows the material found in Chapter 3. In previous videos, we covered Chapters 1 and 2 solutions. And Chapter 3 solutions were maybe a little more involved, at least a few of them, in my opinion. Let's have a quick look at that list of exercises again. So counting them up, you'll see there are 14 problems altogether. The last two were the ones that I found the most tricky. And those involve concepts that are also covered not only in the chapter, but in appendices 3 and 4. So make sure that you read those appendices before trying to tackle these problems. So going back to problem 1, let's get started. And let's jump over to our solution notes. Here we go. Problem 1, Chapter 3 reads, an ordinary electric light bulb is operated under conditions such that 1 ampere of current, 1 coulomb per second, is passing through the filament. How many electrons pass through the filament each second? Remember that the charge of the electron is negative 0.160 times 10 to the negative 18 coulombs. So this problem deals with an old style light bulb. There's a diagram drawn for you right there. By the way, for this problem, you'll find pages 51 to 53 may be helpful. So here's the old style light bulb, and the way these things work is when electricity flows through it, it glows. Well, what's actually happening, it's a thin portion of wire, and I've blown up that part right here. As electricity flows through this, the thin portion of wire heats up and glows. Now the problem says that 1 ampere of current is flowing through the wire. And 1 ampere is the same thing as 1 coulomb per second. So we need to convert 1 coulomb per second to however many electrons per second. And the problem tells us that 1 electron is the same as 0.160 10 to the negative 18 coulombs. But if you look back in Appendix 2, you'll find a more precise electronic charge, which we'll use in the calculation. So this is a pretty simple conversion. You take 1 coulomb per second and multiplying it by the conversion factor of 1 electron over the electronic charge in coulombs, you'll see the coulomb units cancel and you're left with electrons per second, which is what we're trying to calculate. And doing the calculation, 1 times 1 divided by the constant, you get 6.24196 times 10 to the 18 electrons per second. And that is the answer. Exercise 2 reads, according to the law of gravitation, the gravitational force of attraction between two particles with masses m1 and m2, a distance r apart, is g m1 m2 over r squared, where g, the constant of gravitation, has been found by experiment to have the value 0.6673 times 10 to the negative 10 Newton meter squared per kilogram squared. That is, the force of attraction between two particles, each with mass 1 kilogram and distance 1 meter apart, is that many newtons. This last part is just saying if you plug a 1 for both of the masses as well as a 1 for the distance between them, the calculation is trivial and you simply calculate that many newtons. There are 3 parts to the problem. The first says to calculate the force of attraction, electrostatic attraction, between an electron and a proton 10 angstroms apart. Part B is similar, but it has you calculate the gravitational attractive force between an electron and a proton 10 angstroms apart. And it asks about the relationship between the two attractions at that distance. And part C asks about the ratio of the electrostatic attraction to the gravitational attraction and whether or not it depends on distance. Let's start with part A. Calculate the force of electrostatic attraction between an electron and a proton 10 angstroms apart. You'll need the equation for calculating the electrostatic force, and it looks basically identical to the equation for calculating the gravitational force. Here, the constant K is the electrostatic constant, and E1 and E2 are the magnitudes of the two charges, and R squared is in the denominator. R is the distance between the charges. You'll find the electrostatic constant as well as the magnitudes of the two charges in Appendix 2. Plugging in everything, for the electrostatic constant, 8.9876 times 10 to the 9th Newton meters squared per coulomb squared, and then plugging in the two charges in coulombs and 10 angstroms squared in the denominator, but we want the distance to be in meters, so it cancels the meters in the constant. So 10 angstroms is the same thing as 10 to the negative 10 meters. So all of that squared, and you'll see the units now cancel. The 2 coulombs here cancels the coulomb squared, and the meter squared up there cancels the meter squared down there. Running the calculation, you'll get negative 2.3068 times 10 to the negative 10 newtons. The negative symbol means that it's an attractive force. Positive would mean repulsive. For your interest, I've also done the calculation with the two charges, not in coulombs, but in units of stonies. And that's because the text in chapter 3 says that these calculations become simple when you use units of stonies. And the reason is because the constant in units of stonies is simply 1. 1 Newton meter squared per stony squared. You'll need to know what the electron and the proton charges are in stonies, and you can also find that in the appendix. And so plugging in everything, you see the units canceling again. The 2 stonies cancels the stony squared, and the meter squared cancels the meter squared. You're left with newtons, and doing the calculation, you get the same answer. So that's the electrostatic force. Part B is similar, but it has us calculate the gravitational force of attraction, so we'll use that equation. Let's scroll down to part B. Here it is. The force of gravitation is G, the gravitational constant, times m1 times m2 over r squared. And you'll find the gravitational constant as well as the two masses of the electron and proton, all in Appendix 2 again. And so you'll see the units canceling. Kilograms here cancels the kilogram squared, and meter squared cancels the meter squared. You're left with newtons. Running the calculation, you get 1.0165 times 10 to the negative 49 newtons. 10 to the negative 49 newtons. That's tiny compared to the electrostatic force. Now this part also asks, what is the relationship of the electrostatic attraction to the gravitational attraction at this distance? This is asking whether or not the two forces are there. And yes, when you have an electron and a proton 10 angstroms apart, they feel the electrostatic attraction and they feel the gravitational attraction at the same time. And the two attractive forces are simply cumulative. You would add the two. But the electrostatic attraction you can see is much, much greater than the gravitational attraction. The gravitational attraction is almost insignificant. And that leads us to part C, which asks, what is the dependence on distance of the ratio of electrostatic attraction and gravitational attraction of an electron and a proton? And so let's get that ratio, the ratio of electrostatic force to gravitational force. We can put the equation for the electrostatic force up here and the gravitational force down there. And you can see that the r squareds are going to cancel. So there is no dependence on distance. The ratio is distance independent. And we know what the two forces are, so we can plug in those numbers and the newtons would cancel and you'll just be left with the number. And the number is huge. 2.2694, 10 to the 39. So for a proton and electron, the electronic force is 2.2694 times 10 to the 39 times stronger than the gravitational force, no matter the distance apart. Exercise 3 says calculate the velocity with which electrons would move in the apparatus used by J.J. Thomson, operated at an accelerating voltage of 6,000 volts. Assume that each electron has kinetic energy equal to eV, where E is the charge of the electron in coulombs and V is the accelerating potential in volts. Normally EV is labeled potential energy, but this problem has us equate it to kinetic energy of the ejected electron. Let's first look at the apparatus used by Thomson. This is the cathode ray tube that he used to determine the electric charge to mass ratio. The way it works is you have a metal anode separated from a metal cathode, and a large applied voltage between them causes electrons to jump from the cathode and accelerate towards the anode. The little hole lets the electrons pass through and eventually strike this screen over there, the fluorescent screen. And with a large magnet, as well as an adjustable voltage between these two metal plates there, Thomson was able to control the angle of deflection of the electrons. Measuring the angle of deflection as well as the adjusted electric field here, he was able to calculate the ratio of charge to mass. We're not doing that calculation in this problem. Here we simply want to know what the velocity is of the ejected electrons as they travel towards the anode. So let's do that. We set EV equal to the kinetic energy, and we know the expression for kinetic energy from physics, 1/2 mv squared, where little v is the velocity. Solving this for the velocity, we get velocity equals the square root of 2e big V over m. And plugging in everything, 2 times the electronic charge times the applied voltage, 6,000 volts, over the mass of the electron in kilograms. The units will give us meters per second, and you can see that if you know what a volt is. A volt is a newton per coulomb, which is the same thing as kilogram meter squared per second squared per coulomb. And plugging in those for volts, and you'll see the cancellation, and the square root gives us meters per second. Running the calculation, we get 4.5942 times 10 to the 7 meters per second. Now that's a really fast velocity. It's almost the speed of light. And in a couple of problems from now, Pauling will tell us that if the velocity of the particle is more than 10% of the speed of light, we ought to use the relativistic correction. So let's do that. You'll see this method on page 52, and let's compare the two equations. So we have EV on the left, and here the kinetic energy is much more complicated than it was before. So m naught is the rest mass of the electron, c is the speed of light. So we see that there and also down there. And then the v here, that's the velocity. Solving this complex expression for velocity, here's what we get. And then plugging in everything, the speed of light there and there, the rest mass of the electron, the applied voltage, and the electronic charge, and here are all the values that you use. You get these three from Appendix 2, and the problem gives us that. You plug everything in, and you'll end up with 4.5542 times 10 to the 7 meters per second. Let's compare that with what we got before, 4.5942 10 to the 7 meters per second, and now we get 4.5542 10 to the 7 meters per second. So it is a little bit different, and the relativistic correction does need to be used. So that's it for this video, these first three problems in the chapter. The next video we'll go through the next 2 or 3 problems or so, and I hope you join me for that. Take care.